So this might look kind of funny to have a little piece of twine here on my paper, but it's really going to help us start to get familiar with something called an ellipse. So let me just do this, if I can do it carefully. And then let's go to the other side. Let's go here. And it's not perfect, but it does give you a little bit of an idea as to this specialized oval shape called an ellipse. Now, there's a couple points in here that are of particular interest. The point where I have this taped down, those 2 points are called foci. So we're going to learn some stuff about foci. But before I get started on that, let me ask you kind of an unrelated question, or a seemingly unrelated question, especially because this isn't a class in paleontology or anything like that. What was it that killed the dinosaurs? Yeah, an asteroid. So that asteroid hit in the Yucatan Peninsula in the Gulf of Mexico. So right there, a city called Chicxulub. And anyways, yeah, that caused, even though it was like 8 miles wide, and our planet is, 8,000 miles wide, it still caused worldwide devastation. So pretty amazing. Now, what's to stop that from happening now? I mean, this is 65 million years ago, but it still could happen now. So people are worried about it. Now, the thing is, comets, asteroids, and the planets, all these things rotate around the sun, not in a circular path, but in an elliptical path. So a couple summers ago, they got interested and say, well, if we spotted a comet and it was headed our way, or an asteroid headed our way, what would we do? So they did this double asteroid redirect test. There's these 2 asteroids that were rotating, one rotating around the other, and they're rotating in an elliptical shaped path. So they flew a satellite into the smaller of the 2 to change its orbit. And they hoped that changing the orbit of the little one would have a progressive tug on the bigger one and change its orbit to see if they could deflect it from, say, crashing into the Earth. So it was called the DART mission. Kind of for giggles, if you want to, Google DART mission NASA, and then press the enter key. Or let's see, maybe I just got to hit the read it. There you go. And you get a nice little boom. So kind of cute. But in any case, asteroids, ellipses are important, and we're going to work with those. To get familiar with those, let's start with some equations. And the first one I want to start with is this one, x squared over 16 plus y squared over 4 equals 1. Now we're going to take kind of a couple looks at the graph of this, but if you were unfamiliar with something like this at all, then a good place to start would be to try and find, say, the intercepts, the x-intercepts and the y-intercepts. Now how do you find, for instance, an x-intercept or a y-intercept? Come on. Yeah, set in x equals 0 and then set in y equals 0. So I'll make myself a little t-table here, x and y. I'm going to set x equal to 0. I've got this equation, x squared over 16 plus y squared over 4 equals 1. This is kind of a standard form that you're going to want to have your equations in when you're working with ellipses or, in the next section, hyperbolas. But if I set x equal to 0, then I just get 0 squared over 16 plus y squared over 4 equals 1. So basically y squared over 4 equals 1 because this whole term is a 0. To solve here, what I could do would be to multiply both sides by 4 and get y squared equals 4. If y squared equals 4, what could x equal? Oh, thank you for that, plus or minus. Yeah, it could be plus or minus 2. So 2 or negative 2. Now let's do the same thing, except this time we're going to set, say, y equal to 0. So I'll put in a 0 for my y. And let's see if we can't figure out what's going to happen there, I'll end up with x squared plus, or x squared over 16 plus 0 squared over 4 equals 1. And a similar thing is going to happen in terms of solving. X squared over 16 equals 1. Bless you. X squared equals 16. So x equals, what would that be? Plus or minus 4. So you've got two solutions there, 4 and negative 4. Okay, that's great. Now those actually turn out to be special points. And in this section and in the next section, all our conic sections are going to be centered at 0, 0. But from 0, 0, you move to the right by 4 and to the left by 4 to get a couple vertices, and then up 2 and down 2 to get the other two vertices. And then you carefully play a little connect the dots in a nice, smooth, college-educated way to get your graph of an ellipse. Wonderful. But that felt a little bit too slow to do it that way. So let's see if we can't speed that up a little bit. And to speed that up a little bit, I'm going to rewrite this. I'm going to write it as x squared over 4 squared plus y squared over 2 squared equals 1. So that's looking better. Okay. Now how does that help us? Does that help me get to the graph a little bit easier? Well, if you look, what number do you see underneath the x squared? You see a 4 squared. How far did I move to go from the center of this to my vertex in the x direction?
4.
A distance of 4. 4 to the right and 4 to the left. Oh. And then up 2 and down 2. So it was convenient to rewrite it, and it's going to be convenient for you to rewrite it so that you don't have to necessarily solve some equations like this to figure out where the vertices are going to be. Instead, what you're going to do is just look at the number that's underneath this. So you rewrite it as x squared over 4 squared plus y squared over 2 squared. And now you can just look at these numbers in order to try and find the vertices, up 2 and down 2 in the y direction, to the right 4 and to the left 4 in the x direction. Great. Great. Now there is one more thing that we're going to have to get familiar with about ellipses, and that's going to be something called the eccentricity. I'll work on that at example C. Are we okay with this one for now? Looking good on that? Let's move to example B. Now right away you're like, okay, I'm going to use the lessons from example A to work on example B, and that's great. We can write this as, say, y squared over 3 squared. But what am I going to do about the x squared term?
1 squared.
Yeah, we'll think of it as 1 squared. So, excuse me. So see if you can't use this and graph it here.
Would it work if you put it on the other side?
If what?
Would it work if you put it next to the 1? So you would have to change the sign?
The only way you're going to get it next to the 1 is if you move it to the other side, but that would change things up a little bit. I mean, it's still the same equation, I guess, but what tells you how far to go is the number in this denominator. So I would stick with it over here, but I mean, if you wanted to, you could move it around. So Jeff, where do I go in the x direction to find my vertices? How far should I go?
Plus and minus 1.
Yeah, plus and minus 1. So if that's a 2, then halfway should be a 1. Plus and minus 1, good. And Victoria, in the y direction?
3.
All right, thank you. Plus and minus 3. And then as best we can, we're going to play kind of connect the dots. So let's try it like this. And maybe again over here. All right, so the gentleman's agreement I always have with my classes is you don't laugh at my ellipses, I won't laugh at yours. The only thing I really get picky about is when people connect the dots as if it was just like a diamond. if you were to draw, something like that for an ellipse, sharp corners, that's when I get a little bit unhappy. But mostly, if you could do a nice, reasonable job of connecting the dots, that would be great. All right, so let's move on down to example C, and I'll talk about something called eccentricity. So you can jump on the link if you want. There's a link in D2L. There's also the QR code here, whatever works for you. But let's take a look at that and try and understand what something called eccentricity is. So earlier when we were talking about the ellipse, I mentioned that there's these two specific points called the foci. So the foci help determine the shape of the ellipse. That's really, if we're looking back here, that's really where I put down these strings and taped it and then started running things around. I'm not going to work with the formal definition of the ellipse for you. We are going to look at the results. But one thing that's true that you can see at any point on this ellipse, the total distance from here to here and here to here, that distance has to be the same because it's always just going to be the length of the string no matter where you're at. So that's really how you define an ellipse. But in terms of the eccentricity, we're going to need to determine the distance from the center point to these foci. And when you change that distance, it's going to change the shape of your ellipse. Now, if you take a look here, one of my denominators here, I could probably write it as 6 squared. 6 squared like that. And maybe be a little bit more familiar to us based on our previous example. But its ratio, this denominator to this denominator, that ratio is going to give us our eccentricity. Right now it's about 0.48. So as I move this closer and closer to x equals, or to 6 here in the denominator, what's happening to the shape? What's happening to the shape as this gets closer and closer to, yeah, it's expanding. Now over here, when I move A to something really, really small, you got kind of a cigar shape. As opposed to this, what do you think would happen if I take this all the way to 6 in this denominator? What's this shape going to be? It's no longer going to be an ellipse, or I technically will be, but what happens? That's now a circle. So a circle is really a special case of an ellipse. It's a case when both of these denominators happen to be the same. So we separate that out. And those two foci points kind of coalesce into one point, and that point is just center of your circle. So that's an example of the eccentricity. You've got some other examples down here. The planets orbit the sun in an elliptical shape, and that elliptical shape is pretty nearly circular, less than an eccentricity of 0.01. Pluto, remember what happened to Pluto a bunch of years ago? Pluto kind of got demoted, It's no longer a planet. They call it a plutoid, a plutesimal, a planetoid, Plutino, all kinds of different things. But in any case, part of the reason it got demoted is because its orbit was rather eccentric. It had an eccentricity of like 0.3 or something like that. Anyways, let's work on determining the eccentricity and finding out the foci of an ellipse. So this is example C. I guess I can put that one here. Example C. X squared over 25 plus y squared over 9 equals 1. So at least we're starting out with something that looks reasonable, something we can work with. Probably I'd rewrite this right away. X squared over 5 squared plus y squared over 3 squared equals 1. So we can at least determine the vertices of our ellipse. And I don't think I gave you any spot to graph this, so sorry, life goes on. But I do have some rulers up here if you want to borrow one. let's see about drawing this. Now, is it going to be taller or wider? Which one do you think it's going to be? Wider, yeah, because in the X direction we're going to move a distance of 5, in the Y direction we're going to move a distance of 3. So you'll draw something that's a little bit wider than it is tall. So up 3 and down 3 in terms of your vertices in the X direction, or excuse me, in the Y direction. Up 3, down 3, and then to the left 5 and to the right 5. So something like this. Nice. Now we have to determine the foci. And to determine the foci, so foci, you're going to need to determine C. The foci are going to lie along what's called the major axis. So the major axis is the longer of these two axes. So that's your major axis. Major axis. What do you think I would call things in the X or the Y direction? If this is the major axis, what's the other one?
Minor.
Yeah, it's the minor axis. All right, I'm not going to draw that one in. But the foci will lie a distance of C away from the center along, I probably shouldn't have tried to squeeze that in, along the major axis. Now that distance of C is determined this way. C squared equals B squared minus A squared, or A squared minus B squared, whichever one is positive. Now that's assuming that your ellipse is in the shape of x squared over a squared minus y or plus y squared over b squared. But I'll let you catch up to this first. So once you've got it in this standard form, then you can determine what C is. You're eventually going to have to take a square root somehow, but you're going to first start by subtracting the squares here in the denominators. You're going to subtract them in whatever order makes that a positive number, because we want to take the square root of a negative number to find C. We don't want an imaginary distance to work with. Thank you. All right, so let's take a look at x squared over 5 squared minus, or excuse me, plus y squared over y squared over 3 squared. I'm too anxious to calculate c squared. C squared is going to be the 5 squared minus 3 squared, which is 25 minus 9, or 16. If c squared equals 16, then c equals, you'd be right to say plus or minus 4. There's nothing really wrong with the plus or minus 4. The distance of C is how far we're going to have to move away from the center to find our focus. So you can think of it as moving 4 to the right and 4 to the left. So that'd be a nice interpretation for your plus or minus C. If on an exam you just said C was 4, that's fine. You're still going to find the foci by moving that distance away from the center. So we're going to have a point at 4, 0 and negative 4, 0. Looking good there. And while we're at it, let's label the vertices of the ellipse as well. You've got one up here at 0, 3, one down here at 0, negative 3, negative 5 and 0, and finally 5 and 0. So yeah, pretty much everything I could ask for in terms of graphing and labeling an ellipse, including the foci. So we'll call it F1 and F2. All right. How are we looking at example C? A little heads up from Yasser, thank you. All right. Anything on example C before we move on to example D? All right, well, let's take a look at example.
Where did you
Yeah.
get the 16 from?
The 16? It was the 5 squared minus 9, or 25 minus 9 was our 16. So it's always this, the difference in the denominators, or the difference of the denominators, in whichever way makes that difference positive. So if I did it the other way around, I would have had a negative number. Let's take a look at example D. (2x squared plus 25y squared equals 50). Okay. Looking good there, except there's a problem. It's not quite in that nice, neat form that I've had some of these other ones in. I mean, like the first one, we were able to write it as 4 squared and 2 squared. And then the previous one, we had 5 squared and 3 squared, but that's not what I got going down here. So what could I do? Any suggestions as to how I could whip it into that form that I really want in order to see the graph of my ellipse? At least what I think is an ellipse. How could I, let's see, well, what are the things I need? I need a 1 on the right-hand side. I need some square terms here. Now, as far as getting a 1 on the right-hand side is concerned, you have a couple choices. You could subtract 49, but that wouldn't help because it'd just be a mess over here. Or you could divide by 50. So, okay. Now when you divide by 50, let me help you out on the right-hand side. That would be a 1. On the left-hand side, 2 cancels into 50 25 times. So I have x squared over 25. And then y squared over 2. So looking a lot better, looking a lot closer to what I've come to expect, but I'm going to run into a problem underneath the y's. Underneath the x's, I've got a 5 squared, but how about underneath the y's? Ah, well done. You're going to take and square the square root of 2. Now when you take trigonometry, you're going to get pretty good with the square root of 2. In fact, half of the square root of 2 as well. But the square root of 2 is about 1.414. So why would I want that? Why do I care about that? Well, it's going to help me in terms of graphing this ellipse. Like the last one, this one's going to be wider than it is tall, because in the x direction I've got a 5, in the y direction I got the square root of 2. So let's again try and graph something here. And I'm not just going to try and scale it too much. I'll just put a couple tick marks, hopefully equal distance away from each other, roughly speaking. On an exam, I would give you a graph already drawn in as part of your exam, so you don't have to necessarily draw your own scales here. One thing that's kind of a clue when I do that, if your graph doesn't fit on the paper that I provided, the space I provided, then one of us has made a mistake, and I'll let you decide who you think is more likely to be making that mistake. So we've got some points here at 0, 5, excuse me, 5, 0, negative 5, 0, 0 and square root of 2, and 0 and negative square root of 2. Let's find our foci. Are the foci going to lie along the x-axis or the y-axis? The x-axis. Have to be there. Let's calculate c squared. C squared is going to be 5 squared minus the square root of 2 squared. You could also subtract 25 minus 2. You're going to get the same thing. C is going to equal the square root of 23. Okay. Square root of 23 is going to be a little bit less than 5. It's actually probably closer to this than I'm drawing. So I'll have negative square root of 23 and 0, and positive square root of 23 and 0 for my foci. And that's pretty much it. Pretty much all I could ask for in that kind of a problem. Oh, there is one last thing that I'll do here. Let's find the eccentricity. And the eccentricity is going to be the ratio of this distance to the longer side. So it's going to be, the eccentricity is going to be C over the longer side. So in this case, it's going to be A, which is going to be square root of 23 over 5. So a pretty eccentric ellipse. The closer it gets to 1, the more drawn out and cigar shaped it's going to be. And I'm just kind of curious what that would be numerically. So let me open up my software. Actually, I think you can probably get it done on my calculator before I get it from my software. About 0.96 maybe. Square root of 23 divided by 5. Yeah, there we go, about 0.96. Okay, so we got the eccentricity. We're in good shape. You're always going to take that C and put it over whatever is the larger denominator term, larger squared term. So in this case, 5 was bigger than the square root of 2, so that's where I found my ratio. There's a lot of comets that have really long orbits. Most people, if they're familiar with any comet at all, will be familiar with Halley's Comet. And Halley's Comet returns in about every 75 years, 76 years. So got a little ways to wait for Halley's Comet. A couple more here. Example F. Well, going to need to do some playing around with example F. Example F is not in anywhere near the right form. Unfortunately, we've got a 1 on the right-hand side, but we don't have those things as denominators. So what are we going to do? Let's catch up with our ellipses here. I think I've got some of these graphed already. So here's your graph for E. That number is as advertised, square root of 2, negative square root of 2, etc. This one, well, kind of strange. And actually pretty small, isn't it? I mean, compared to the last one, yeah, that one starting to look like the evil eye. It's kind of funny. In any case, I've got to rewrite this into standard form. The standard form for an equation of ellipse is x squared over a squared plus y squared over b squared equals 1. Now that's if your equation, or if your ellipse is centered at 0 and 0. So standard form of an ellipse. All right, so nice, standard form ellipse, but this is not looking anything like that standard form. So there's a little trick involved. Last chance for somebody to say, oh, I got it, I got it. All right, not happening this morning, that's all right. So the trick is to rewrite this as x squared divided by 1/9. And y squared, or to divide by, in the case of y squared. Yeah, 1/4. Now I still need to play with this a little bit. I still want this to look like something squared here. So what would that squared thing be? What would I square to get 1/9? Not quite. I appreciate the effort there. Well, tell you what, it has to be a fraction, right? Let's take it a piece at a time. What do you square to get the 1? 1. What do you square to get the 9? 3. What should I put underneath the y here? Yeah, 1/2. And again, that would be squared. So, whew, a little extra work there, but now that's making sense. Where should I find the ellipses, or excuse me, the vertices in the x direction? So if I go back to my graph and I zoom in a little bit on this and I click on these, what should I see here? 4. Yeah. You're going to see the decimal value, like Justin said, 0.33333, and negative of that decimal value, up and down for 1/2. Let's determine the foci and see if we can't figure out those as well. So for the foci, we have to do a little thinking here. So for the foci, so this is example F. Foci are going to be b squared minus a squared, or a squared minus b squared. Which of these is bigger? The denominator of the y squared or the denominator of the x squared? Yeah. 1/2 is bigger than 1/3, so c squared equals 1/2 squared minus 1/3 squared. Now 1/9 minus 1/4. If you're getting a little squeamish, like, oh, I really hate fractions, no worries. You can do that on your calculator. Let's just do 1/4 minus 1/9, and you're going to get a decimal value, but then you can hit the answer to fraction key to figure out that I think it should be like 5/36 or something like that. Let's just double check here. Math, answer to fraction, bam. There we go. So we get 5/36. But that's c squared. What's c equal to? Yeah, root 5 over, excuse me, the square root of 35, or 5 over 36, which is root 5 over 6, just like Jeff said. Nice. So our foci are going to lie a distance of square root of 5 over 6 above and below 0, 0. So our foci are going to be at these points. And have them at 0 and square root of 5 over 6, and 0 and negative square root of 5 over 6. So those are where my foci are going to lie, for example, F. I'll give you a second to copy these down, then we'll take a look at the actual graph. Wrong one there. And let's zoom in a little bit. Let's turn on these points. Uh-oh. They lie outside my ellipse. What's wrong? Oh, those are graphed in the wrong order. Or did I make another mistake? Here, let's take a look here. 9, no. Yeah, so these are graphed in the wrong order. That's because the 0 should be first. Now, I can't remember when I put this together if I intentionally did that or was it an actual mistake. But what I do want to point out is if you make a mistake with your foci, you could end up with ellipses or foci outside the ellipse. And if that happens, there is a mistake. Your foci should lie inside the ellipse. So when we saw foci outside the ellipse, you know right away that there's a mistake. they should lie along the major axis of your ellipse. So there we go. That's looking a lot better. F1 and F2. And then everything else is as predicted. Right here and then above at half and -1/2. Okay. Looking good. Just a couple more here to finish up. Let's see. Okay. For example, H, and I think the graph kind of covers up a little bit of it. Let's see. No, we're on example G. So let's do example G first, and then we'll do example H. So for example G, you've got an ellipse here. They tell you that the focus is at 0, 2, and at this point is 2, 0. That's a vertex. Let's see if we can't use that information to try and figure out the equation of that ellipse. So this is example G. So I know that in general I'll have x squared over something plus y squared over something. Can anyone tell me either of these somethings? What does one of these have to be? Dylan? Yeah, has to be 2 squared plus, for lack of anything better right now, we'll call it b squared. But we got another clue here. And one thing that I always remind students is that in a math problem, if they give you some information, you generally need it. There's been like one exception in my entire math career that I've seen where you got something you actually didn't need. So that little exception doesn't apply here. Here we need this. It's going to help us find B. How's it help us find B? Well, which one of these has to be bigger? B or the 2? B. Because the major axis is in the y direction. So that's going to give me c squared equals b squared minus 2 squared. The larger one minus the smallest one. But wait, I know something about c. What does c have to equal? Yeah, this distance, that has to be c. c is equal to 2. So I can plug that in. 2 squared equals b squared minus 2 squared, or 4 equals b squared minus 4. 8 equals b squared, so b equals the square root of 8. Yay. And that pretty much gives me my answer here. The only thing left to do is just to plug it back in here, and I'll end up with x squared over 2 squared plus y squared over the square root of 8 squared equals 1. Now, I have been asked a lot of times, does it matter to me if I put a 8 down there, or do you want square root of 8 squared? It doesn't matter to me much. The only bummer about putting, just an 8 in here is that then you got to think a little bit when you graph it. You don't want to graph things in the y direction, up 8 and down 8. It should be up square root of 8 and down square root of 8. So it's up to you. It's how careful are you? And I'm not going to mark you wrong if on a test you give me this answer as opposed to this answer. I'll probably write the answer key this way, but it's your choice. Comments on example G here. Let's try example H. This is find an equation whose graph is shown. You've got a vertex here at 15 and 0. And unlike the last problem, this problem passes through the point 10 and 5. Well, let's see here. What can I tell myself to start with? What do I know here? I'm trying to determine this equation. Do I know anything that can help me out? Jeff? Yeah, perfect. That's going to be x over 15 squared plus y over, call it b squared, equals 1. Great. So I know that much. Let's take a look at it here. So here's my graph. And I've got to adjust the graph of b, or I've got to adjust this value of b so that this graph actually passes through that point. So somewhere along the line, I'm going to get the Goldilocks of values for b. It's going to be just right. It's going to pass through that point. So 6.7, probably not it, but it's probably pretty close. Let's actually figure out the exact value. But how do I do that? What am I going to do to figure out that exact value? This is the piece of information that I know and I haven't used yet. How can I use that?
Plug it into X and Y.
Yeah, exactly. Thank you. There's your X and Y coordinate. That has to fit into this equation. So it's going to be 10 squared over 15 squared and 5 squared over b squared. That's going to be 100 over 225 plus 25 over b squared equals 1. Let me move that to the other side. So in terms of solving, I'll get 25 over b squared equals 1 minus 100 over 225. I could think of that as 225 over 225 minus 100 is going to give me 125 over 225. So at least I'm closer now. How would I finish this up? What would you do? Multiply both sides by b squared. Let's also multiply by 225 at the same time. Since you have something equals something else, this is a proportion, and you can solve by cross-multiplying, or at least start to solve. So 25 times 225 equals 125 times b squared. You got a lot of 25s here. If you wanted to divide out one, that's fine. Let's just divide both sides by 125 and get 25 times 225 divided by 125. Let's see, that's going to be about 45, I'm thinking. So that's going to be, yeah, it's got to be 45 equals b squared. So square root of 45 equals b. And remarkably, and really cool, square root of 45 is about the 6.7 that we were seeing on our little slider. So cool. Let's not forget to put down our final answer. Our final answer for something like this, I'll put it up here, is going to be x squared over 15 squared plus y squared over the square root of 45 squared equals 1. That's what I would hope to see for a final answer from you on a problem like this. Yeehaw. All right. Not too bad. Not too bad. Comments or thoughts on example H there? All right. Let's put this one to rest.